Hello and welcome to Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss the latest fan efficiency requirements and technology advances. The Air Movement and Control Association, or AMCA, estimates that fans consume between 30 and 40% of commercial HVAC energy. Therefore, improving fan efficiency is an important step toward reducing overall energy use. So on today's program, we'll review the latest fan efficiency requirements and then discuss some recent technology advances that can help improve fan efficiency. To cover this content, we have Trane application engineers Dustin Meredith and John Murphy. So Dustin, can you start us off with the latest ASHRAE 90.1 requirements that address fan efficiency?
Sure, Jeannie. Because the energy use of a fan depends heavily on the design of the air distribution system, simply requiring a minimum fan efficiency alone is not sufficient. As a result, ASHRAE Standard 90.1 prescribes a maximum allowable limit on the overall fan system power when that system exceeds a 5 horsepower threshold. This standard includes two options for compliance. Option 1 is based on nameplate motor power, while Option 2 is based on fan brake horsepower. Option 1 is easier to apply and easier for a code official to verify, but Option 2 is more flexible. This is the table that's included in the standard. For either of the two options, it prescribes a limit on fan system power as a function of the maximum supply airflow rate. You will notice that there are separate columns for constant volume or variable volume systems. The power limit is more stringent for constant volume systems. And the text of the standard states that single zone VAV systems must comply with the more stringent constant volume limit. Before getting into some examples, let me point out that this requirement does have some exceptions, which we've paraphrased here. The first is for hospitals, vivariums, or labs. If the system includes exhaust or return flow control devices used to maintain space-to-space pressure relationships, then it's allowed to comply with the less stringent fan power limit for variable volume systems. And second, individual exhaust fans that are 1 horsepower or less do not need to be included in the sum for fan system power. Finally, remember the 5 horsepower threshold that applies to this whole section of the standard. Small systems that are below this threshold are exempt from this fan power limit. Next, let's return to the table and look at an example.
To comply using Option 1, the sum of the nameplate motor horsepowers for all the fans in the system must be no greater than the value listed in the table. For example, if the design supply airflow rate for a VAV system is 30,000 CFM, the total allowable nameplate motor horsepower is 30,000 times 0.0015, which equates to 45 horsepower. Now, Option 2 is based on the input power of the shaft, or brake horsepower. For the same example of VAV system, the total allowable fan system brake horsepower is 39. Now, this is less than the 45 nameplate horsepower allowed by Option 1, which may allow for any belt or drive losses, motor inefficiency, or safety factor in motor selection when using Option 1. But Option 2 also includes this adjustment factor A to account for special circumstances. A second table in the standard includes the adjustment factors for things like fully ducted return or exhaust systems, return or exhaust control devices, high efficiency filters or air cleaners, heat recovery and evaporative cooling devices, or even sound attenuators. These pressure drop adjustments then become a credit that increases the allowable fan system power. To demonstrate, consider if our 30,000 CFM VAV air handler includes a MERV 13 filter and a total energy wheel. The pressure drop adjustment for the MERV 13 filter is 0.9 inches of water. And for the total energy wheel, the adjustment is based on the effectiveness of this device and then applies to each airstream. Starting with the filter, it's installed in the mixed airstream, so the design airflow through it is the full 30,000 CFM of supply air. Based on this airflow and the 0.09 pressure drop adjustment, the resulting credit is 6.5 brake horsepower. Next, for the wheel. its effectiveness is 70%. So the pressure drop adjustment is calculated to be a little over 1 inch. At design conditions, the outdoor airflow through the supply side of the wheel is about 10,000 CFM, so the horsepower credit is calculated to be 2.5. The airflow through the exhaust side of the wheel is only 8,000 CFM on this side, so the horsepower credit for this side is 2.0. Summing up the credits for the filter and both sides of the wheel, the total adjustment or credit is 11 horsepower. So the allowable fan system brake horsepower for this example is increased to 50, compared to only 39 if no adjustments were made. Note that this is also higher than the 45 nameplate horsepower limit allowed by option 1. So for applications that have one or more of these items listed in the adjustment table, option 2 provides greater flexibility to account for those devices.
With the power limit calculated, next question is, what does standard 90.1 mean by the term fan system? Does this limit apply to each separate fan, all the fans in the building, or what? The answer is found in the definition section of the standard. Here it clarifies that this fan system power limit applies to the sum of all fans that are required to operate at fan system design conditions. And it includes all fans that are used to supply air from the heating or cooling source to the conditioned space. Then, either return that air to the source or exhaust it outdoors. And there's another definition to clarify what's meant by fan system design conditions. This is the time when the system is delivering its highest supply airflow rate to the conditioned spaces. This typically occurs in the summer at peak cooling load conditions, but for some applications, it could be at peak heating load. Let's look at a few examples to better understand these definitions.
Here's a central VAV air handling unit that includes a supply fan and a return fan. Both are used to supply air from the heating and cooling source to the occupied space and then return that air to that source. The highest supply airflow rate occurs at peak cooling load conditions, and at that time, both the supply and return fans will be operating. So in this case, you would need to add the fan powers for both the supply and return fans together when each is operating at design conditions. Then that sum cannot exceed the limit calculated using either option 1 or option 2 in the table. As for this local exhaust fan, remember the exceptions that Dustin described earlier. If this fan is 1 horsepower or less, it does not need to be included in the sum. Let's change this example by adding fan-powered terminals to each of the zones. In this case, the series fan-powered terminals would need to be included in the sum since the terminal fans operate at cooling design conditions and assist in supplying air to the conditioned spaces. However, the parallel fan-powered terminals would not need to be included in the sum since their fans only operate in the heating mode and not at cooling design conditions. Let's change the example again, but this time the central VAV air handling unit includes a central relief fan instead of a return fan. In some applications, this relief fan only operates when the airside economizer is activated. In that case, its power would not be included in the sum for the system since it does not operate at cooling design conditions. However, in other applications, this central relief fan may operate at cooling design conditions to control building pressure and then must be included in the sum. But in that case, this fan will likely operate at a much lower airflow and use less power than when operating in the economizer mode. This often causes confusion on how to apply the fan power limit to this type of system. To explain, let's look at some example numbers. The supply fan is selected to operate a design supply airflow of 30,000 CFM, which occurs at cooling design conditions in the summer. Its brake horsepower is 32.2. The central relief fan is selected to deliver 27,000 CFM, which occurs during economizing mode. At this airflow, the fan power is 16.6 horsepower. If you add these two numbers together, you'll be well above the limit of 39 horsepower using option 2. But the relief fan will only be operating at this power when airside economizing during mild weather, not at cooling design conditions. At design conditions, this fan will be only moving 6,000 CFM, which corresponds to a power of 0.2 horsepower. Therefore, total fan system power at design conditions is 32.4. So when you have a central relief fan, you want to make sure you're using the fan powers at cooling design conditions, not during economizer mode. Now, the last example I'll share is a dedicated outdoor air unit that supplies conditioned air to multiple zones. Each zone is equipped with some type of terminal unit that also contains a fan. This might be a fan coil, water source heat pump, VRF terminal, or something similar. For this configuration, the 90.1 user manual clarifies that each terminal unit is considered a separate fan system because each has a separate cooling or heating source. In this case, the power of the dedicated outdoor unit fans must be allocated to each of the terminal units on a CFM weighted basis. In this example from the user's manual, a wing of an elementary school uses 8 water source heat pumps, each with a 3/4 horsepower fan motor. A dedicated outdoor air unit supplies 500 CFM of outdoor air to each of the 8 classrooms. This dedicated unit is equipped with a 5 horsepower supply fan and a 3 horsepower exhaust fan. Since each classroom receives 1/8 of the total outdoor airflow, then 1/8 of the fan power for the dedicated outdoor air unit is added to the fan power of each water source heat pump. When we do this allocation, the total power for each fan system is 1.75 horsepower. Since this is under the 5 horsepower threshold for this section, these fan systems do not need to comply with the fan power requirements of standard 90.1. The 90.1 user's manual is a good source for clarification. It includes several examples for applying this fan power limitation. I've included some excerpts and references in your handouts to support the examples I just shared.
Before moving on to fan efficiency itself, when option 2 is used, standard 90.1 has a requirement related to the motor selection. Based on the required brake horsepower, the standard requires you to select the first available motor size that's larger than the brake horsepower. However, the exceptions do allow for selecting one size larger to allow for some safety factor if the brake horsepower and nameplate are close enough. Next, in addition to limiting fan system power, the 2013 version of standard 90.1 now also includes a requirement for the efficiency of the fan itself. It uses the metric fan efficiency grade, or FEG, which is defined by AMCA standard 205. The FEG must be 67 or higher in order to comply with this new requirement.
To determine FEG, the fan's peak aerodynamic efficiency based on total pressure is compared to this chart, which is published in AMCA 205. For example, consider a 25-inch diameter fan with a peak total efficiency of 68%. This point falls above the FEG 71 line, but still below the FEG 75 curve. Therefore, this fan has an FEG of 71. This FEG classification is determined by the fan manufacturer, so the system design engineer need only filter available selections based on the minimum FEG required by the code or standard.
But FEG is an indicator of peak fan efficiency, not actual operating efficiency. So then the second part of this new requirement is to select the fan such that at its design operating condition, its total efficiency is within 15 percentage points of its maximum efficiency. Using the previous example, if a fan's maximum total efficiency is 68%, it would meet this requirement as long as its total efficiency is 53% or higher at the selected design operating point. But like other sections of standard 90.1, there are several exceptions to this new FEG requirement. First, small fans are exempt. If an individual fan or fan array has a combined nameplate horsepower of 5 or less, it does not need to comply with this requirement. Next, if the fan is included inside a piece of equipment that's already listed in section 6.4, then it does not need to meet this requirement either.
Section 6.4 of the standard is where you find the tables listing the minimum efficiency requirements for equipment such as packaged rooftop units, water source heat pumps, air-cooled chillers, PTACs, and VRF systems. Since this equipment already has an overall minimum efficiency requirement, the fans that are included in these products are currently exempt from having to also meet the minimum FEG requirement. In addition, fans that are included in equipment that already bears a third-party certified seal for energy or air performance are also exempt. Most air handling products bear a certified seal from ASHRAE. Cataloged air handlers and blower coils are certified to ASHRAE standard 430. Likewise, fan coils and unit ventilators are certified to ASHRAE 440. Therefore, most of the fans in these products are currently exempt from this new FEG requirement. But there is some nuance to this.
For cataloged air handlers, ASHRAE 430 only certifies the performance of the supply fan. So for air handlers that also include a return or relief fan, the supply fan would be exempt from this new FEG requirement, but the return or relief fan would not. Also, custom air handling units do not typically bear an ASHRAE seal. So most custom manufacturers will need to incorporate fans that meet this new FEG requirement. FEG provides users with a simple classification system to segregate fans based on peak aerodynamic efficiency. However, FEG is not without its limitations. I recently wrote an engineer's newsletter that explains the strengths and limitations of FEG and also describes some newer metrics, such as the performance-based efficiency requirement and fan efficiency ratio. These metrics are being considered to address the shortcomings of FEG, so you might be hearing more about them in the future. This newsletter is listed in your bibliography and is available at trane.com if you want to learn more.
Thanks, guys. In the first part of this program, we reviewed the latest energy code requirements related to fan power and efficiency. Now we'll discuss some of the more recent fan technology advances and how they can help improve efficiency, lower sound levels, reduce space requirements, or some combination of these benefits. So Dustin, back to you.
Thanks, Jeannie. Some of these fan technology advances are more recent than others, but they all change the way that fans are selected and applied for efficient operation. We'll start by discussing the application of direct drive plenum fans and fan arrays. Then we'll talk about optimizing the process of motor selection and motorized impellers. After that, we'll discuss some of the issues related to selecting fans and air handlers that have varying aspect ratios and methods for vibration isolation. Historically, most large fans used in HVAC systems have used a drive kit consisting of one or more belts and associated sheaves to connect the motor to the fan shaft. However, as variable frequency drives have become more cost-effective and reliable, direct drive fans have become more popular, direct drive plenum fans in particular. With the direct drive plenum fan, the fan wheel is mounted directly on the motor shaft. With no belts or sheaves and fewer bearings, direct drive fans are more reliable and require less maintenance than belt drive fans. And since there are fewer moving parts, no belt-related drive losses, and less inlet or outlet obstructions, direct drive plenum fans are typically more efficient, quieter, and experience less vibration than belt drive plenum fans. Because the motor is in line with the direction of airflow through the air handling unit, the motor being mounted behind the fan wheel does not restrict airflow, does not stick out the side of the unit, and does not increase unit width. However, the air handling unit may need to be slightly longer to accommodate the motor mounted behind the fan wheel. This can be partially offset by using a fan array or motorized impellers, two subjects to be discussed later. Depending on the location of the fan within the air handling unit, a plenum fan may be more or less efficient than a house fan. Let's take a look at a few example selections. A house fan is specifically designed to discharge into a long, straight section of duct that is about the same size as the fan outlet. This minimizes energy loss as velocity pressure is converted to static pressure and turbulence off the fan dissipates into laminar flow. With this discharge configuration, a housed airfoil fan will typically require less power than a plenum fan.
For these examples, we're using a typical VAV air handling unit operating at 13,000 CFM and a total static pressure of 3.8 inches. For this first configuration, where a draw-through supply fan discharges into a straight section of duct, the housed airfoil fan requires 11.8 brake horsepower, compared to 14 for the belt-driven fan and 12.8 for the direct drive plenum fan. While the housed fan requires less power, the plenum fan will typically have significantly lower discharge sound levels. The reduced sound levels occur partly because air velocity dissipates more quickly as the air pressurizes the plenum surrounding the fan, and because the plenum provides an opportunity for some of the sound to be absorbed before air discharges from the unit. The direct drive plenum fan reduces sound levels even further because it does not have the belt-related drive losses and associated noise, and because there are no obstructions in the inlet and the motor is mounted behind the fan wheel, it does not restrict airflow leaving the fan. Of course, this chart compares discharge sound. On the inlet side, plenum fans will usually have a higher sound levels than housed fans. Depending on the fan's location within the air handling unit, either discharge or inlet sound may be more important. So the quietest fan choice depends on the application.
So, if the air handling unit has a draw-through fan that discharges directly into a sufficiently long, straight section of duct that's about the same size as the fan outlet, a housed airfoil fan will typically require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels. Let's look at another example. A discharge plenum is often added downstream of a housed fan to reduce discharge sound levels or to provide more flexibility, like multiple duct connections or to allow for an abrupt change in direction. But as I mentioned, a housed fan is at its best when discharging into a straight section of duct. When a housed fan discharges into a plenum, the energy losses result in increased fan power.
In our example, adding a discharge plenum to the housed airfoil fan increases its brake horsepower from 11.8 to 13.2, since it no longer discharges into a straight section of duct. This is still lower than the belt drive plenum fan, but now the input power for the direct drive plenum fan is less than the housed airfoil. But adding the discharge plenum does allow the housed airfoil to now achieve discharge sound levels that are fairly close to the plenum fans. In this example, the direct drive plenum fan is still the quietest, especially in these low frequency octabands that are difficult to attenuate.
So, when a discharge plenum is added to a draw-through housed fan, it results in more fan power being consumed, typically to the point where a direct drive plenum fan has about the same power consumption as the housed airfoil fan. And discharge sound levels are similar, if not better, with the plenum fan. But the air handling unit with a plenum fan will likely be shorter. In this example, adding the discharge plenum to the housed fan increased the overall length of the air handling unit by more than 3 feet. When multiple supply duct connections are desired, a housed fan requires a discharge plenum to allow for the multiple connections. With a plenum fan, multiple duct connections can be made to the fan section itself, eliminating the need for a discharge plenum and resulting in a shorter unit. Due to installation restrictions, it's often unlikely that a housed fan can be installed in the ideal configuration as shown in example 1. This makes the use of discharge plenums and multiple supply duct connections fairly common. Let's look at one more example. In some applications, final filters are included as the last section in the air handling unit. When a housed fan is used, a diffuser section must be added downstream to provide even airflow through the final filters. This is not a requirement for a plenum fan, since it pressurizes the surrounding plenum. This provides even airflow through the filters with minimal downstream distance.
In this configuration, the input power for the housed fan increases due to the added pressure drop of the diffuser section and the fact that the housed fan is no longer discharging directly into a straight section of duct. For our example, the direct drive plenum fan requires the least amount of power, 14.1 horsepower versus 15 for the housed airfoil fan.
Let's summarize this discussion of housed versus plenum fans. When discharging into a single, sufficiently long, straight section of duct that is about the same size as the fan outlet, a housed fan will likely require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels. If a discharge plenum is added downstream of a housed fan to reduce sound levels or to allow for discharge flexibility, a direct drive plenum fan will likely require less power than a housed airfoil fan, with similar or superior discharge sound levels. Additionally, the plenum fan will likely result in a shorter air handling unit. When downstream sections are present, such as a discharge plenum, final filter, gas heater, or even a blow-through cooling coil, a direct drive plenum fan will likely require less power than either a housed or belt-driven plenum fan. Before we leave the discussion of plenum fans, the use of direct drive rather than belt drive plenum fans have allowed for some changes to traditional paradigms when selecting the fan. Historically, the diameter and width of the fan wheel would often be predetermined by the manufacturer of the air handling unit. The variable open to change was the rotational speed of the fan shaft, or RPM, which was adjusted using belts and shifts. Today, direct drive plenum fans are available in various wheel diameters and wheel widths. Even though there are no belts and shifts to adjust speed, the fan can be operated at various speeds by a VFD. In a sense, the VFD on a direct drive plenum fan replaces the drive kit that would be used for a belt-driven fan. Most people think of a VFD as being used to reduce the speed of the fan, from the motor's synchronous speed to some minimum turn-down limit of the VFD. However, the VFD can also be used to operate the motor above synchronous speed. This provides the opportunity to use one of two selection approaches. The first, which we'll refer to as synchronous speed selections, operates the motor at its synchronous speed, typically 1800 or 1200 RPM. The diameter or width of the fan wheel is then changed to achieve the desired performance. Flexible speed selection is a relatively new concept in the industry. With this approach, the width of the fan wheel is held constant, and the diameter or speed of the fan is then changed to achieve the desired performance. As an example, the VFDs and motors that Trane uses for direct drive plenum fans in air handling units can operate up to 90 or even 120 Hz if torque is properly accounted for. Flexible speed selection typically allows for a more efficient fan choice. And because the fan operates at a reduced speed with a wider wheel, the flexible speed selection will typically result in lower sound levels. One final way to characterize centrifugal fans is whether a single fan wheel or a multiple fan array is to be used. Historically, most air handling units have used a single fan wheel, although the use of a few fans in parallel has been somewhat common. In the past decade or so, this concept has been taken a step further, and the use of 4 or more fans in an array has increased in popularity. A fan array uses multiple, smaller fan wheels arranged in parallel airflow paths, with direct drive plenum fans being typical. The example in this picture shows 4 stacked direct drive plenum fans in an array. Fan arrays have some advantages over using a single fan wheel, but they also have drawbacks. The primary benefits of a multiple fan array include a possible reduction in overall length of the air handling unit and redundancy in the event of a failure. Let's look at these two benefits in more detail. The distance or spacing required both up and downstream of a fan is typically defined as a function of the fan wheel diameter. Therefore, if multiple small diameter fan wheels are being used, the up and downstream spacing required will usually be less than if a single large diameter fan wheel. In many cases, this can shorten the overall length of the air handling unit. However, there is a bottom threshold to this length reduction. There is a certain amount of space needed upstream or downstream to allow the fans to be serviced or replaced, if necessary. This includes space for a person and for a fan motor and/or wheel when the fans are stacked in multiple levels. It may also require space for a ladder and possibly a mechanical hoist. To demonstrate this potential to reduce unit length, let's look at another example.
For this example, an air handling unit is selected to deliver 15,000 CFM, and the fan is located upstream of the cooling coil. When a single 33-inch diameter fan wheel is used, the minimum spacing required upstream is 19.8 inches. If 2 smaller fan wheels are used in an array, the upstream spacing is reduced to 14.7 inches. As the number of fan wheels continues to increases, this upstream spacing continues to decrease. But you can see that the incremental benefit is greatest going from 1 to 2 fans, and not so much as the number of fans continues to increase. But as Dustin mentioned, there's a certain amount of space needed to allow the fans to be serviced. The typical recommendation for upstream clearance is 18 inches, but in this example, we use the absolute minimum of 12 inches. You can see here that when 4 fans are used, this upstream spacing required for service is longer than the spacing dictated by the fan wheel diameter. So in this case, there's no further upstream length reduction benefit by using more than 3 fans.
The story is similar for the downstream side of the fan. Here is the result of adding the upstream and downstream distances. When a single fan wheel is used, the overall length of the fan section is about 74 inches. If two smaller fan wheels are used in an array, the overall unit length is reduced to about 57 inches, assuming access doors on both sides of the unit. While the length can be reduced significantly by changing from 1 to 2 fans, the potential length reduction diminishes as the number of fans continues to increase. And, like in this example, due to the need for service access, the length might actually increase when more fans are used. When more than about 4 or 6 fan wheels are used in an array, the upstream and downstream spacing requirements begin to be dictated by the need for service access rather than by fan wheel diameter, so there is typically little further length reduction benefit. And as I mentioned, another benefit of using a fan array is that it can provide some level of redundancy. If one fan fails, the other fans are still able to provide some or all of the airflow. Of course, this assumes that the fans were selected to provide this redundancy up front.
Using the same 15,000 CFM air handling unit, this table shows the redundancy that can be achieved by using 2 fans in an array. The first row shows a selection at design conditions with both fans operating. Each fan delivers 7,500 CFM and requires a 7.5 horsepower motor. In order to provide 100% redundancy, if only one fan is operating, the other fan must be able to deliver the design airflow all by itself. So as shown in the second row, if either one of the fans is to deliver 15,000 CFM all by itself, it must be equipped with a 20 horsepower motor, not the 7.5 horsepower motor. For this example, a 2-fan array can provide 100% redundancy as long as each fan is provided with a larger motor. Of course, the drawbacks to the increased motor size are reduced motor efficiency and increased size of the electrical service. Let's look at a 3-fan array. At design conditions with all 3 fans operating, each fan is selected to deliver 5,000 CFM and requires a 7.5 horsepower motor. If anyone, as shown in the second row here, as any one of the fans was to fail, the remaining 2 fans could still achieve the full 15,000 CFM. Each fan is able to deliver 7,500 CFM using the same 7.5 horsepower motor. The same is true for the 4-fan array. If any one of the fans was to fail, the remaining 3 fans could still deliver the design airflow without the requirement to upsize the motor during selection. So any of the configurations in this example can achieve 100% redundancy. The 2-fan array requires the lowest total horsepower when all fans are operating, but it requires equipping each fan with a larger motor to provide 100% redundancy. Either the 3 or 4-fan array can provide 100% redundancy without changing the motor sizes, but require more power than the 2-fan array.
While fan arrays have some advantages, there are some drawbacks compared to a single fan configuration. Likewise, when a multiple fan array is needed, there are advantages of using fewer, larger fans, like 2, 4, or 6 fans, versus many smaller fans, like 9, 12, 24, or even more. So let's summarize the factors for consideration when comparing a single fan to both multiple fan strategies. A fan array will typically reduce the overall length of the air handling unit. The length reduction by going from 1 to 2 fans is great, but the incremental length reduction benefit is not as significant as you continue to increase the number of fans. Eventually, you hit a minimum threshold dictated by service clearance. Using a single fan wheel will typically result in the lowest cost air handling unit. When a fan array is desired, using fewer, larger fans will typically cost less than using many smaller fans. When multiple fan wheels are used, the air handling unit can provide some level of redundancy. Of course, this requires proper selection to ensure that when one fan fails, the remaining fans are able to provide the required airflow. In most cases, an array of 3 or 4 fans is able to provide the same level of redundancy as an array with many smaller fans. Using a single fan will typically require less power than an array with multiple fans. When a fan array is desired, using fewer, larger fans will typically require less power than using many smaller fans. Since the fans are operating at a slower speed and the larger fans are more efficient, a fewer number of fans will often have better acoustics. This isn't a certainty, however. The sound spectrum changes enough when more fans are added that a comparison of quality sound data should ultimately determine the best approach for the application. Another benefit of using a fan array is easier serviceability. When multiple smaller fans are used in an array, the fans and motors are lighter and easier to replace, if ever necessary. Fewer moving parts, and therefore fewer fans, generally results in better reliability. Of course, the redundancy provided by using multiple fans partially offsets the concern over fan failing. Trane has published an engineering bulletin that goes into more detail on all of these advantages and drawbacks. Also, the examples that John and I went through during this program are included in an engineer's newsletter, if you want to review them in more detail. Both of these publications are listed in your bibliography. The market for air handling equipment has been trending not only towards direct drive, but also towards a more flexible, custom-type product in general. With this change comes new fan options and challenges to consider. So let's discuss a few of the more important advances. First, motor sizes can now be optimized for the specific application. Next, there's even an option to integrate variable speed control into the fan assembly, something known as motorized impellers. We'll end this program with a brief discussion on the impact variable aspect ratio has on unit performance and the various vibration isolation methods you might encounter. Let's start with optimized motor selection. Consider a fan with a brake horsepower requirement of 5.85. Using traditional NEMA motor horsepower increments, this fan needs more than 5 horsepower, but less than 7.5 horsepower. Thus, a 7.5 horsepower motor would traditionally get selected. With optimized motor selection, we can move beyond NEMA increments. Assuming half horsepower increments, we could use a 6.5 horsepower motor for this example. The principle is to take advantage of the motor-specific application. In an air handler, the motor is typically inside the casing, operating in a conditioned space under a variable torque load. In this specific application, the motor is able to handle much more than its nameplate power, generally up to 50% more. This enables incremental motor sizes that are in between the traditional NEMA increments. Note that an optimized motor isn't necessarily operating in the service factor. The service factor is meant to provide a means to operate a general-purpose motor beyond nameplate conditions for a short period of time. An optimized motor is technically operating in a definite purpose application and has been tested within that application.
This chart depicts the efficiency of a 7.5 horsepower motor. The y-axis is motor efficiency and the x-axis is motor load as a percentage of the nameplate full load. In general, motors will operate near peak efficiency between 50 and 100 for 50% motor load. Below 50%, the motor efficiency starts to drop off dramatically, and there's also a little bit of drop off above 100% load. Using the example Dustin just showed, if the fan requires 5.85 brake horsepower at design operating conditions, one would normally select this 7.5 horsepower motor since the nameplate exceeds the brake horsepower requirement of the fan. The motor load at these design conditions is 5.85 divided by the 7.5 nameplate, which equates to 78% motor load. Note that the motor efficiency at this design load is 91%, which is pretty close to the motor's nameplate efficiency, which is based on 100% motor load. But in a VAV system, the fan will operate at reduced airflow for much of the year, and the power drops off exponentially with this airflow reduction. As an example, for a single-zone VAV system, at 70% of design airflow, fan power decreases to 2 brake horsepower, which is 27% of the nameplate motor load. At this reduced load, the efficiency of this example motor drops to 86%. Now, optimized motor selection takes a general-purpose motor, then evaluates and approves that motor for use at higher loads for the specific use of driving a fan located inside an air handling unit. Here's the efficiency chart for a 5 horsepower general purpose motor that's been evaluated and approved for use as a 6.5 horsepower motor. At our example design conditions of 5.85 brake horsepower, the motor efficiency is slightly lower, about 89% compared to 91% for the larger motor. But the apart load efficiency is better, 88% compared to 86% with a larger motor. And this part load efficiency difference will be even greater at lower fan airflows.
Smaller motors are generally less efficient than larger motors. And since an optimized motor selection takes advantage of operation above a motor's full load, it will usually have a slightly lower efficiency at design load, but part load efficiency should be better. Being able to right-size a motor can ensure connected load costs are minimized. Smaller wiring, fuses, VFDs, and such. They improve serviceability because you're using physically smaller motors. And as we showed, this approach will also serve to optimize part load efficiency. Now let's see how this optimized motor selection can help meet the fan power limitation of ASHRAE 90.1. If you use option 1, which is based on motor nameplate, it's easier to comply with since we have additional smaller incremental motor sizes to choose from. Using the previous example, the motor nameplate is only 6.5 when using optimized selection versus 7.5 when using traditional NEMA size increments. If you use option 2, which is based on brake horsepower, the method used to select the motor has no impact. This option only considers the shaft input power downstream of the motor. To meet the intent of the standard, be sure to select no more than the next NEMA horsepower increment above the brake horsepower. For example, if the brake horsepower is 5.85, no more than a 7.5 horsepower motor should be used. Any increment including and between 5.85 and 7.5 horsepower can be used, just don't exceed 7.5 horsepower. As I mentioned earlier, there has been a rapid trend to use direct drive plenum fans over the last several years rather than belt drive or house fans. In fact, roughly half of all air handler sales volume now use these fans. As we discussed, this type of fan has been attractive from a customer's perspective because it is quiet, efficient, can offer redundancy, and minimizes maintenance expense. But there are a number of customers who don't value these benefits enough to pay the premium required to purchase a unit with a direct drive plenum fan. This premium includes the cost of the fan, the motor, the variable frequency drive, and the cost of any required unit length. As a result, many customers continue to use lower cost house fans for price sensitive jobs. A motorized impeller is a type of direct drive plenum fan that can help address these concerns. It's an integrated assembly that consists of a direct driven impeller, an electronically commutated motor, or ECM, and a variable speed drive all in one package, which result in a much shorter overall unit. This integrated assembly, along with the reduced length, often enables a motorized impeller to reduce installed cost and allow for a smaller footprint. Likewise, some applications require a vertical fan inlet orientation, something that a traditional direct drive plenum fan offering does not typically or cannot address. But there are some additional considerations. Motorized impellers tend to top out around 5 inches of static pressure, so they may not be suitable for higher pressure systems. Next, as we will discuss shortly, there may be better performing fan choices available. And finally, the replacement cost of a fully integrated assembly can be quite high. Motorized impellers perform well, but there are some trade-offs when compared to the best DDP fan systems. When analyzing the efficiency of a fan system, one must consider all inefficiencies involved. First, there's the efficiency of the fan impeller itself. Motorized impellers utilize a high efficiency backward inclined impeller. Thus, the aerodynamic efficiency of the impeller should be similar to a DDP fan. However, the external rotor motor can reduce the overall fan efficiency since it protrudes through the fan inlet. Next, there are losses associated with the drive kit. Of course, direct drive fans do not have any losses here. Then there's the efficiency of the motor. Electronically commutated motors are brushless DC motors that utilize permanent magnets in the rotor to increase power density and reduce loss when compared to AC induction motors. Typically, 20 to 25% of the internal losses of an AC induction motor are attributed to the windings in the rotor. Much of this loss is eliminated by replacing the rotor windings with permanent magnets in the EC motor. Optimally designed stator windings, along with greatly reduced rotor losses, result in a motor that is more efficient and physically smaller than an AC induction motor of equivalent output power. Finally, there's the efficiency of the variable speed drive. A motorized impeller uses an electronically commutated motor that is very similar in operation and efficiency to a VFD. Like a motor, variable speed drive efficiency is a function of the load. The nearer the controller is to full load, the more efficient it will operate. The integral variable speed drive is engineered to match the EC motor and ensure that the combination is as efficient as possible during normal operation. Fan schedules and selection programs traditionally reference motor nameplate power or fan shaft power. However, motorized impellers are rated in input power to the motor controller, not fan shaft power. This means that a distinction needs to be made between fan impeller energy requirements and electrical sizing. The fan shaft power, or brake horsepower, is generally used to compare the energy requirements amongst a number of fan options. It is also used to size the motor. The motor nameplate horsepower is then included in the schedule. However, there is another useful definition of power: input electrical power, or kW. As we saw earlier, there are a number of inefficiencies not present when the fan shaft power is being evaluated. The input kW includes the missing inefficiencies associated with the motor and motor controller. So with a traditional direct drive fan, the user will select a motor based on the brake horsepower. The VFD and wiring between the two are sized based on the motor nameplate or max applied motor horsepower. The upstream electrical service is then sized based on the VFD line input current. With a motorized impeller, the motor and the variable speed drive are an integrated package. The upstream electrical is simply based on the motorized impeller line input current. The brake horsepower is not needed for electrical sizing. Thus, the only accurate way to compare a motorized impeller with another fan type is to measure the input energy to the other fan type. However, the high variation among components and a lack of a complete test standard make this a difficult task to accomplish. To enable this comparison, some manufacturers will provide an estimate of fan shaft power for motorized impellers. For upstream electrical sizing, however, the motorized impeller line input current should be used. It's important to note that an estimate of the missing losses can be calculated using AMCA Standard 207, and ASHRAE Standard 1210 provides a method to evaluate VFD efficiency. As these standards mature, the comparison of different fan types should shift to focusing on input electrical power rather than brake horsepower.
To demonstrate the benefits of motorized impellers, let's compare two outdoor air handling units, each equipped with a supply and a return fan array. This first air handler uses traditional direct drive Plenum fans, a 2-fan array for the supply and a 2-fan array for the return. Notice the return fans are oriented horizontally, and that this inlet plenum also serves as a section to house the internally mounted VFDs for both supply and return fans. Now this second air handler uses motorized impellers for both supply and return, again each being an array of 2 fans. Notice how the motorized impellers allow the return fans to be oriented vertically, which avoids the need for an upstream plenum section. Plus, there's no additional space required for variable speed drives, since that control is integrated into the fan assembly itself. When we compare the performance, the unit with a traditional direct drive Plenum fan has a combined brake horsepower of 17.1, compared to 18.2 for the unit with motorized impellers. Now remember, motorized impellers measure input kW, so shaft brake horsepower is an estimate. So brake horsepower is about 6% higher, but look at the reduction in the overall unit length and cost from using the motorized impellers. The vertical orientation of the impellers and the fact that the motor is partially slid inside the impeller results in a 30% reduction in overall unit length and a 20% reduction in cost. So when budget and space are tight, motorized impellers can be a valuable option to minimize cost and length while still providing good efficiency.
The fact that motorized impellers are rated in terms of input kW can make it more confusing when determining whether a system complies with the fan power limitation of ASHRAE 90.1. Again, option 1 is based on the motor nameplate horsepower. The UL standard for air handling units requires that a motor horsepower be reported on the unit nameplate. For motorized impellers, a conversion from input kW to horsepower is typically used for the unit nameplate. So for a unit with motorized impellers, a nameplate horsepower is reported similar to how a traditional direct drive Plenum fan with factory installed VFD is reported. In our previous example, the input power to the supply fan array was 11 kW and also 11 kW to the return fan array. So the total horsepower on the nameplate would be 14.8 for each array. Keep in mind that this value includes variable speed drive and motor losses, so you might have a higher nameplate horsepower when using a motorized impeller compared to a traditional direct drive Plenum fan. However, it could be lower if the direct drive plenum fan had to jump up to the next higher NEMA horsepower increment, from 7.5 to 10 horsepower, for example. If determining compliance using option 2, use the estimated brake horsepower for the motorized impeller. In our example, we estimated the brake horsepower of the supply fans to be 10.1 and 8.1 for the return fans. Let's now briefly cover 2 additional topics that become more important as units get more flexible: the impact variable aspect ratio has on unit performance and the various vibration isolation methods you might encounter. Historically, cataloged air handlers have been designed to a fixed aspect ratio, width versus height. But more recently, a trend has been to offer some variability in this aspect ratio to better meet space restrictions on a job site. That is, you can select an air handler that's short and wide or tall and skinny. The challenge is that the spacing between components, such as the distance between a cooling coil and the fan inlet, or between the outer edges of the fan impeller and the surrounding cabinet wall, impact fan performance and efficiency. With a fixed aspect ratio, this impact can be more easily tested and predicted. But for a variable aspect ratio unit, the industry tends to rely on some common rules of thumb. For example, the recommended minimum distance between the outer edge of the fan impeller and the surrounding cabinet is often kept at half the fan wheel diameter or greater. And the minimum distance between the fan and upstream or downstream components is generally 1 fan diameter or greater. For a fan array, a separation wall or counter-rotating impellers can be used. In either case, there are minimum separation distances between the impeller and wall or between impellers. These rules of thumb are generally followed by a custom air handler manufacturer to minimize any negative effects on the fan. However, they might be overly conservative or not be conservative enough. The good news is that much work has been done in this area to better understand how the cabinet affects fan performance. ASHRAE-sponsored and in-house manufacturer testing has narrowed this gap of understanding. The results of ASHRAE Research Project 1420 were presented in 2015. This project explored a number of system effects related to plenum fans and in particular focused on uniform cabinet sizing relative to the fan. Some manufacturers have taken this a step further and tested a variety of air handler configurations to fill many of the gaps in the ASHRAE research. Using AHRAE test standards for airflow and sound performance, an air handling manufacturer can vary the parameters of an actual unit and optimize the fan and cabinet for each application. An air handler manufacturer can use this information to improve on the conventional rules of thumb and optimize equipment performance. Another option to consider is vibration isolation. A direct drive fan will offer results superior to a belt-driven fan, but vibration isolation may still be needed in some applications. With this in mind, let's discuss the various vibration isolation methods. Unfortunately, there's not one right answer. All methods, including no isolation, have some benefits, and all have some drawbacks. Isolation can be offered internal or external to the unit. Both reduce structure-borne issues, and both will minimize the need to lock out VFD frequencies that excite building resonances. Internal isolation has the added benefit of reducing casing-radiated sound levels and minimizing the need to lock out VFD frequencies that excite unit resonances. However, external isolation has the added benefit of higher isolation efficiencies. Many manufacturers offer direct drive fans with little to no isolation, especially when offered in an array. If the application is right, no isolation is desirable as it results in a minimized footprint and a turnkey solution for the installing contractor. Fan arrays present an additional method. Each fan can be isolated individually or they can be isolated as a group. These slides illustrate the various isolation methods available for an example 6-fan array. Internal isolation is available for each fan individually, or the entire array can be isolated. If a higher vibration efficiency is desired, the fan array air handling unit can be isolated externally. Lastly, no isolation results in a minimized footprint and a turnkey installation. In addition to whether and which isolation method to choose, the ultimate consideration should be performance, specifically sound performance, as inadequate vibration isolation can generate noise. To help make the best decision on which isolation method to choose, be sure to request quality sound data taken in accordance with AHRAE Standard 260. Then simply compare the unit sound power levels with the job requirements. Note that it's not as easy as simply removing the isolation hardware and retesting. A unit designed for a particular isolation method must have had any issues encountered evaluated to ensure smooth performance, both acoustic and vibration, throughout the operating range.
Thanks, guys. We hope today's program helped you learn more about fan efficiency and technology. As always, the bibliography included in your handout provides more information on where to find a number of the resources related to today's topic, including the Engineering Bulletin and Dustin's Engineers newsletter. For those of you seeking continuing education credit, be sure to check out our online continuing education programs. They include many past ENLs, all free and on demand. And don't forget to fill out a survey and let us know what you think of today's program. AIA members, please remember to turn in your member information to your local site coordinator. And finally, please ask your local host about details for the remaining Engineers Newsletter Live program this year. We have one more ENL on acoustics for outdoor applications. So please plan to join us. Thanks for your time today, and we look forward to seeing you later this year.